Hello everyone, I'm Songsong from Wuhan University. It's my pleasure to introduce our new work towards an efficient weighted random walk formulation. This is a joint work with RMIT University and Huawei. We first introduced the problem definition of we introduced two weighted random walk models before introducing the problem definition. For probability-aware random walk model, uh, the edge weight denotes the probability that a node chooses or affects its labels. Um, but the edge weighted denote indicates the cost of moving one node to its labels in cost-aware random walk models. Then we compute the expected cost for U to hit S via weighted random walk model in two similar ways for two weighted random walk models. Based on this, we introduce our problem weighted random walk formulation. The input of our problem is a weighted graph and a budget B. The output of our problem is a key-size node set S belongs to V that can maximize the budget B to be received. Analysis shows the objective function of our problem is mononomial and submodular. This problem is critical to a range of real-world applications, such as advertising in social networks and telecommunication base station selection in wireless sensor networks. In social network, the page browsing process can be modeled by probability-aware random walk model. Then, our problem is equivalent to how to select pages in the network so that other users can easily browse these pages. In wireless sensor networks, the data transmission can be modeled by cost-aware random walk model. Then, uh, our problem is equivalent to how to choose a load set at base station to minimize the energy cost. Next, we introduce our solutions. We first give an overview of our solutions. This table shows that the time complexity and guarantee of our solutions when they apply to weighted random walk domination problem over probability-aware random walk model and cost-aware random walk model respectively. Our solutions are based on a greedy framework. We select a load with the largest marginal gain in each iteration. Then the result can achieve 1 minus 1e approximation ratio. The main challenge to solve our problem is how to compute CUSB effectively. To overcome this challenge, we devise the dynamic programming-based solution and matrix-based solution. Then we introduce the dynamic programming-based selection DpSel. We use a recursive manner to compute CUSB. Here, we show how to get the total time complexity of DpSel step by step, but it's too slow for practical using. To improve the efficiency of DpSel, we devise the matrix-based selection MatrixSel. The core idea of this solution is calculating the CUSB of all nodes that at the same time by the matrix. Any work steps after S is visited will have no effect on computing CUSB. We reconstruction the transition matrix P as a trapped model. Here, QS hat represents the subtransmission matrix corresponding to S hat. Then we introduce how to compute CUSB and based on QS hat. First, we find the length of random walk equals to the sum of frequencies of random walk reaching node. Inspired by this observation, we prove the sum of the use though our NS hat is equal to CUSB. Then we can compute NS hat I to get CUSB of all loads at the same time. Next, we introduce how to compute NS hat I. First choice is computing QS hat B directly, but matrix multiplication is very time consuming. Then, how to avoid calculating QS hat B and get NS hat I directly and quickly is very important. We use matrix multiplication vector and iterative calculation to solve this problem. For MatrixSel, the total time complexity is OKBNM. It needs to uh, compute NS hat n O(n) times in each iteration. To further improve the efficiency, we try to find some way to avoid calculating the marginal gain of all those in each iteration. So we devise the bound-based selection BoundSel. The core idea of this method is proving the loads if the marginal gain around I less than or equal to the upper bound of the marginal gain around I minus 1. But this strategy cannot work for the first round. To estimate the upper bound of the first round marginal gain of nodes, we propose this lemma. To apply our solutions to weighted random walk domination over cost-aware random walk model, we transfer an weighted graph to an unweighted graph by adding nodes. Then we have the expected heating step from U to S in an unweighted graph is equals to the is equal to the expected heating cost in an edge-weighted graph. Finally, we show our experiment results. We use 9 real-world datasets in our experiment. We compare 6 algorithms in our experience. DpSel, MatrixSel, and BoundSel are proposed methods in this work. Uh, Here pictures show the efficiency of solutions over probability of real random walk. We found BoundSel and MatrixSel consistently beat the SamSel and DpSel on all datasets. These two pictures show the efficiency of solutions over cost-aware random walk. We find BoundSel, MatrixSel, and SamSel are almost identical and constantly beat DpSel on all datasets. These two pictures show the effectiveness of solutions over a probability of real random walk. Here pictures show the effectiveness of solutions over cost-aware random walk. From these two pictures, we find BoundSel, MatrixSel, and DpSel have the same gain and constantly beat other methods on all datasets. To evaluate the scalability of our solutions, we vary n from 50,000 to 250,000. When n is equals to 150,000, BoundSel can return the results in a reasonable time, but SamSel takes almost 4 hours to return the results. Okay, thank you for your listening.